Hey everybody, Mrs. Bixler here, and we are cruising through Unit 5, and now we're going to be talking about parallelograms. And as I mentioned before, parallelograms are shapes where parallel lines come into play, which is so exciting. So let's jump right in and just talk about initially the definition of a parallelogram. So a parallelogram is a special kind of quadrilateral, and in this quadrilateral, it is made up of two pairs of parallel sides. Those are obviously going to be the opposite sides. So I've got that guy is parallel to that guy, and this one is parallel to this one. That is it. That is the definition of a parallelogram. It's a quadrilateral with two pairs of parallel sides. That's it. We're going to learn about properties later, but so right now, if you would like to open up geogebra.org/classic and try to create a parallelogram. So you want to make a quadrilateral with two pairs of parallel sides. And then I want you to mess around with that and see if you can come up with properties of parallelograms. What are things that you think make sense about that parallelogram? So hopefully you've spent a little bit of time on GeoGebra, just kind of messing around, and we're going to be doing this in class as well. But hopefully you noticed the very first property of a parallelogram, and this is actually the definition of a parallelogram. So this would be the definition of a parallelogram. And we actually abbreviate parallelogram as like a teeny tiny little cute parallelogram, which is so cool. So the definition of parallelogram is a quadrilateral with both pairs of opposite sides are parallel to each other. So hopefully you notice too, you've got both pairs of opposite sides are congruent. So again, we've got both pairs of sides in both of these situations. Both pairs of opposite sides are congruent to each other. All right, there is more. There are in fact three more. Hopefully you notice that both pairs, again, both pairs of opposite angles are congruent. And then if you messed around a little bit more, you could have noticed that the same side angles are supplementary to each other, which makes sense, right? Because we've got two parallel lines and they're cut by a transversal. The same side interior angles are going to be sup. Same side sup. Sup. All right. So that's the fourth one. And the fifth one, and this one's a little bit harder because I didn't offer you any direction here. But the fifth one is that the diagonals bisect each other. And I know we've talked about this kind of casually in class, but now we can see it a little bit better, especially when we mess around with GeoGebra. So these are the five properties of parallelograms. Again, the first one is the official definition of a parallelogram, and then we've got the properties as well. All right. Now, more than just the opposite angles being congruent to each other, remember, we're dealing with parallel lines here. So if I crisscross, I've got my little diagonals, watch what happens. Not only is this angle congruent to this angle, but I've created smaller angles thanks to my diagonals. And watch this. If I know this line is parallel to this line, and here's a nice little transversal, I know this angle is congruent to this angle because of AIP. What else do you think is true? Yeah, this angle is congruent to this angle. This angle is congruent to this angle. And this angle is congruent to this angle, all because of AIP. That's not technically a property of a parallelogram, but we would just say, like if I was saying, you know, that this angle is congruent to this angle, like in a proof or something, I would just say AIP. But it's kind of cool, right? So now instead of just having two pairs of opposite angles being congruent to each other, we have more, which is pretty awesome. All right, so awesome. All right, so I want you to pause the video here and try this proof. Go! All right, we're back. So hopefully you jumped right in and you threw your givens onto the figure. So you were told that this whole thing is a parallelogram, and you were told that PJ and KR are congruent to each other, or the measurements are equal. And we want to prove that SJ and KQ, those segments are equal, their measurements are equal. So hopefully right off the bat, you wrote down your givens, and then you had to shake out that given a little bit. So, oh, wait a second. I know that SP and QR are congruent to each other because that is a property of a parallelogram. And then, ooh, I know that angle P and angle R are congruent because opposite angles in a parallelogram are congruent. And you actually literally would like write that down. There's like a little bit of abbreviation, but no like SAS equivalent. Sorry. All right, and then looky loo, we know that these two triangles are congruent to each other because of SAS. If you want to confirm that with yourself, you always can go back through and just double check. We've got a side, we've got an angle, and we've got another side. So I know those two triangles are congruent because of SAS, and then ba-ba-da-ba, CPCTC, we're done. Nice little 5-step proof, but you've got a lot of power, right? Knowing that something is a parallelogram gives you a lot of information. All right, scooching on. So now, let's say I told you right before that we had a parallelogram, right? So then you knew like opposite sides were congruent, opposite angles were congruent, etc. If you know it's a parallelogram. Now, as always, we're going to do the converse, right? So now I give you a random quadrilateral, and you don't know necessarily that it's a parallelogram. How do you think you can prove that something is a parallelogram? I want you to pause the video and think about it. I broke it into chunks for you. All right, we're back. So hopefully you figured out, well, I know that if I can prove that both pairs of opposite sides are parallel to each other, I know it's a parallelogram. That's the definition of a parallelogram, right? Another way is I can prove that both pairs of opposite sides are congruent. So that's kind of nice. That's another property that we have. But then here's something unique. I can prove that one pair of opposite sides are both parallel and congruent. So just one pair are both parallel and congruent. Then I know that my shape is a parallelogram. All right, moving on to diagonals. Hopefully you figured this out. If I can prove that the diagonals bisect each other, then I know that it's a parallelogram. And the last one is if I can prove that both pairs of opposite angles are congruent to each other, then I know it's a parallelogram. So make sure you feel really, really good about this. Pause the video for a little bit if you want to, and just make sure you understand these 5 ways to prove that something is a parallelogram. Because we're going to jump into this proof. So pause the video and try it. All right, we're back. So right off the bat, I hope that you threw all of your givens onto the figure. So I know right now that is all the stuff that I'm going to put in here. So I know that angle 1, ooh, that changed color, that's exciting. And angle 2 are congruent to each other. And I know that this big mama is a parallelogram. So remember, you have a lot of power there. So I've got my givens. And again, I sort of did like the quick way, right? This is just like the flow of my reasons. And then I know that AB and DC are congruent to each other because opposite sides in a parallelogram are congruent. And if we're trying to prove that this smaller quadrilateral in the middle is a parallelogram, we've got a bunch of different ways we can do that, right? So I'm going to try and see if I can prove either like opposite sides are congruent to each other, or maybe I can prove opposite angles are congruent to each other. And so a nice little way to do that is to figure out, are there any triangles that I can prove are congruent, and then do a little CPCTC. So then, a little AIP, look what happens. I know that this angle is congruent to this angle. So now look what I've got here. I have that those two angles are congruent. It just changed color again. So I know that my angles are congruent, and then I've got another set of angles. So why are those two triangles congruent to each other? Because of ASA. Woohoo! So now think about it. We have a lot of information. We now know that those two triangles are congruent to each other. And right off the bat, I can do a little CPC, and I know that BE is congruent to FD. But, is there any way that I can prove that BF, like line segment BF and line segment ED are congruent? That's a little bit harder, right? Because we don't know information about those like upper, smaller triangles. But remember, another method, and this is the weird one, is that you can prove that one pair of sides, are both parallel and congruent. We've already proven that they're congruent. Is there any way that we can prove that they're parallel to each other? Yes, watch this. I'm going to call this angle 3, and I'm going to call this one angle 4. We know that angle 3 and angle 4 are congruent to each other, also because of CPCTC. So we had to use CPCTC twice here, right? The opposite sides are congruent, and then angle 3 and angle 4 are congruent to each other. And then look, what do I know then about, what do I know then about angle 5 and angle 6? Well, thanks to a little subpost and subtheorem, I now know that angle 5 and angle 6 are congruent to each other. So if I know that angle 5 and angle 6 are congruent to each other, that is huge because that tells me that BE and FD are going to be parallel to each other. See this? See how they share side EF? That's the transversal, and it means the two parallel lines are going to be BE and FD. And we know that simply because angle 5 and angle 6 are congruent. I know it's crazy, but you'll kind of get into a groove looking for this stuff. So now we know that it is a parallelogram because we have one pair of opposite sides that are both parallel and congruent. Woo! That's a good one, and it's an exciting one. I love it. I'm also a geometry teacher. Okay, here we go. So there are other theorems that we want to talk about with parallel lines, and these will also be applied to triangles. So in another shape too. All right, so I know that these lines are parallel. This is given to me. And I am told, oh, I lost my letters. So here's R, here's S, and here's T. And then let's call this like ABC. So if I am told that RS is congruent to line segment ST, if these lines are parallel to each other, remember all those like little parallel line theorems that we talked about before, it follows that AB and BC would be congruent. So this is an important theorem here. There's no real cute name here, but just if lines are parallel and they like cut a transversal into congruent parts, they're going to cut another transversal into congruent parts. All right. So I want you to go ahead and pause the video and try this guy. Go. All right, we're back. So hopefully you got that BC is also 8. Hopefully you got that AB is 10. You got that RT is 12 and BC is whoop, whoop, 5x. If you're not sure about that, rewind, go back, look at the previous slide, and then come back to us. All right, so there's something really important in a triangle, and there's something called a midline. And all a midline is the line segment that connects the midpoints of two sides of a triangle. So I could draw any triangle I want. It does not matter what it looks like. If I have the midpoint of this side and the midpoint, I'm like eyeballing here, the midpoint of this side, if I connect those two midpoints, that green line segment, that's what we call the midline. And the midline has some pretty cool properties, and you can kind of see it here. But so here's our if-then statement. Like this is what we call the midline theorem. So if I know that I have the midline, then I know that my midline, DE, is going to be parallel to BC. So I know that DE and BC are going to be parallel to each other. And even cooler, I know that DE is going to be half of the base. And that always happens in every triangle. So the midline is going to be parallel to the base, and it's also going to be half the base. So in general, on the left, do you see how I have the midline, right? I've got the midpoint of one side, the midpoint of the other side. If I know my base is 2x, I know that my midline is going to be x. And in addition to that, I also know that it is parallel to my base. But look at the one on the right. We're not told automatically that this is the midline. However, if I know that I've got a line segment that is crossing the midpoint on one side and it's parallel to the base, if it's crossing the midpoint on one side and it's parallel to the base, then I know it has to be the midline and it's got to be crossing at the midpoint over here. And then what would the length of the base be? 32. Whoop, whoop. Awesome. All right, so the midline is super, super important. Now, in a trapezoid, we have something that seems very similar, but it has a different name. So a trapezoid is a quadrilateral with only one pair of parallel sides. This is really important. So it's sort of like the isosceles triangle definition, right? Where some people say like it's at least two congruent sides. Some people say it's a quadrilateral with at least one pair of parallel sides. I disagree. A trapezoid is a quadrilateral with one pair of parallel sides. So this guy is parallel to this guy. We call those parallel sides the bases. And then we call the sides that are not parallel to each other the legs. Now, the median is just like the midline. I'm going to connect the midpoint of one side and the midpoint of the other side. And then I connect them. This is what we call the median of a trapezoid. And the length, though, of this median is different than the midline for a triangle. So the median is going to be the average of these bases. So if this base is x, let's say, and this base is y, the length of my median is going to be x plus y divided by 2. It's the average. So instead of it being half the way the midline was in a triangle, it's going to be the average of those two. So hopefully that makes sense. So there's the midline of a triangle and the median of a trapezoid. All right, that's it for me. Go tackle the homework. You're going to crush it. And I will see you soon. Thanks.